Hi everyone, and welcome to the first of two videos looking at some past exam questions on concentration time graphs. So you can see we've got a question here that's got a graph on it. It's a graph of concentration against time. It tells us a little bit about what's going on here. A student has carried out an investigation on the rate of reaction. They used a large excess of methanoic acid, which ensured that its concentration was effectively constant. So its concentration is not going to change. During the reaction, the bromine is used up and its orange colour becomes less intense. The intensity of the bromine colour can be measured with a colorimeter. Okay, so that's how they've actually managed to measure the concentration. They've measured the intensity of the orange colour of the bromine, and then as the reaction has gone along, the orange colour is decreased, the concentration of bromine has decreased, and we can measure that over time. Okay. So what do we actually need to do with this question? It says here, we need to do three different things. We need to determine the order of reaction with respect to bromine. We need to work out the initial rate of reaction, and then we need to calculate the rate constant K. So we're going to work through these points in order. The first thing we're going to do is try and work out the order of reaction with respect to bromine. So to do that, we're going to have a look at the graph again. And the way that we're going to be able to work out the order of reaction from a concentration time graph is to work out the half-life of the reaction. Okay. The half-life is how long it takes for the concentration to halve. So we need to work that out from the graph. And to do that, I'm going to pick some numbers where it's going to be nice and easy to see where they halve. So I'm actually going to start here, not at the start of my graph. I'm going to start with 0.008, and we'll talk about why that is in a minute. But all I'm going to do is read across from 0.008 and then read down from my graph where that comes to on the x-axis. Okay, and that's coming out at 10, 20, 30, 40, 50, 60 seconds. Okay, that is not the half-life, okay, because that is not the amount of time it's taken for the concentration to halve. Okay, to work out the half-life, we need to go from a concentration of 0.008 to a concentration of 0.004. Okay, so I'm going to do the same thing. I'm going to read off from there and see what time that leads to. And that then will give us our half-life. Okay, so that is coming out at 250 seconds. So this is our half-life, okay, from 60 to 250. Okay. So we have a half-life here of 190 seconds. Okay. That does not help us on its own work out the order of reaction. We need to measure the half-life again, and we need to see whether the half-life increases, decreases, or stays constant. That's what's going to tell us what the order of reaction is. So to measure the half-life again, I'm going to go from 0.004 to 0.002. Again, how long does it take for the concentration to halve? So I'm going to read across from 0.002. This is why you always want to have a ruler when you're in an exam. And we're at 490, 480, 470 seconds. Okay, and so therefore, this half-life here is 220 seconds. Okay. So it looks like the half-life is increasing, okay, but it's always a good idea to measure 3 half-lives, okay, just to be sure that you've got the pattern right. So I'm going to do the same thing again. I'm going to go from 0.002 to 0.001. If we measure across from here, we just about managed to fit this onto the graph. And that's coming across at the end here. So where are we here? We are at 650 seconds here. So this means that our half-life here is 180 seconds. And so this very nicely shows us then why it's so important to measure 3 half-lives. Okay? If we'd only measured 2, we'd say, oh yeah, look, the half-life is increasing. Okay? When you measure 3 half-lives, you can see, well, actually, the half-life is staying constant, and I've just been a bit inaccurate with my measuring on the graph. Yeah, if I was one small square over, then I'm going to take 10 seconds off, and you probably find the half-life is going to be around 200, 210 seconds-ish on average. So it's really important that you measure 3 half-lives so that you don't get a false idea of what's going on with the half-lives. So I'm just going to write this here. I'm going to say half-life is constant at about 200 seconds. Okay, and how does that help us, right? This is the bit of knowledge that we need to have. We need to know that if you have a constant half-life, that tells you that it's a first order reaction. Okay. So we're going to go ahead and write this here in our answer. So determine the order of reaction with respect to bromine. I'm just going to write this again. The half-life is constant. It's always a good idea to write out what the number is. It doesn't need to be spot on. Half-life is constant at around 200 seconds. Therefore, the order of reaction with respect to Br2 is first order. Okay, remember, if your half-life is decreasing, then that's telling you you've got a 0 order reaction. If your half-life is constant, it's a first order reaction. And if your half-life is increasing, you've got a second order reaction. Okay. So we can now say we've done this bullet point. Next thing we need to do is to determine the initial rate of the reaction. Okay. And how are we going to do that? We're going to go back to our graph again. And in order to work out the rate of the reaction, we need to draw a tangent to the graph and calculate the gradient. Okay. It asked us for the initial rate of reaction, so we want to draw a tangent right at the start of our graph. Okay. So we're going to get our ruler and we're going to try and draw a line that is parallel to the graph at this starting point here. Okay. And you do want to try and match this up as close as you can. If you're slightly out, it makes a big difference. If you see at this end of the ruler, if I slightly move this end of the ruler, this end goes all over the place. Right, so we do want to be careful with trying to line this up here at this end. It is worth just taking a minute to get it as close as you can, because it does make a surprisingly big difference by the time you get down here. Right, so there's my tangent, and I need to calculate the gradient of that tangent, and in order to do that I'm going to do change in y over change in x. The easiest way to do it is what I've done here, just carry it all the way down to the x-axis. Okay, and then if we're going to do change in y over change in x, well, the change in y is going to be from 0.01, right, down to 0. And then to get the change in x, I'm just going to read where does this come out on my x-axis, and that's coming out at 270 seconds. Okay, so we're going to say that the initial rate, and actually I'll just write this on the page here. Okay. So we can say that the initial rate is going to be equal to our 0.01 was our change on the y-axis, change in our concentration, and the change on the x-axis, change in the time, was the 270 seconds. And we end up with a kind of horrible looking number here. We're going to want to put that into standard form. Okay, so I'm going to call that 3.7 times 10 to the 1, 2, 3, 4, 5 minus 5. And if we think about units, it's rate of reaction, isn't it? So it's going to be units of moles per decimeter cubed per second. So that's how we've worked out our initial rate from our tangent. And finally then we need to calculate the rate constant k. Right. How are we going to do that? Well, the rate constant k is part of the rate equation, isn't it? So we're going to write our rate equation here. How do we know what the rate equation is? Okay, well, it depends on the orders of reactions with respect to each reactant. Okay, from what we worked out earlier on, we worked out that the order with respect to bromine was first order. So the concentration of bromine is going to be to the power of 1. And it's telling us up here, because we used a large excess of methanoic acid, the reaction is effectively 0 order with respect to methanoic acid. So we don't need to worry about that. Okay, so this is our rate equation. Then if we want to calculate the rate constant k, we're going to rearrange it. K is going to be equal to the rate divided by the concentration of Br2. What's the rate? We just worked it out, didn't we? We worked out the initial rate of reaction here. So I'm going to go ahead and use that number. And then what's the concentration of Br2? This is a bit less obvious. We need to be careful with what our number here is. Remember, this was the initial rate. So that was the rate at the start of the reaction. So therefore we need to use the concentration of Br2 from the start of the reaction. Okay, if we just flick back to our graph, if you remember, the initial concentration was 0.01. Okay, so we're just going to use that for our concentration of Br2 here. Okay, we can calculate that, but we can see really what's going to happen here. It's going to come out as 3.7 times 10 to the minus 3. Okay. And then, as always, we're going to want to work out the units. We don't write numbers down without units, so we're going to substitute the units in here. Rate was in units of moles per decimeter cubed per second from here. And this was the concentration of Br2, wasn't it? So it's units of moles per decimeter cubed. Okay, this then is just going to cancel out, and it's just going to leave us with units of seconds to the minus 1. And there we go. So we worked out our order of reaction. We worked out that it was first order because we could see there was a constant half-life. Okay, remember we measured the 3 half-lives to make sure that we had the right pattern. We worked out the initial rate of reaction through drawing a tangent and calculating the gradient. And then we worked out our rate constant by rearranging our rate equation and substituting the values in.